Good afternoon. So, last class we discussed proportional controller and PI controller, and we saw that for the proportional controller, using the proportional controller for the first order plant, we were able to shift the pole to the further left by tuning the proportional controller gain. However, proportional controller does not change the type of the system because it does not introduce any poles. Whereas if you go for PI controller introduces a pole at the origin. The advantage is you can get a zero steady state error for step reference input. We obtained the transfer function of the closed loop system, and we compared it with the standard second order system characteristic equation. We derived the expression for natural frequency and zeta in terms of Kp and Ki. So we have two knobs, and we can solve for Kp and Ki given the zeta and omega n. So today we will study PID controller. That is, we will include one more knob, which is KD. So Kp plus Ki by S plus Kd into S. So output of in the unity feedback structure, output of the controller is called as the control law, which becomes the input to the plant system. Difference between the reference and output is the error, and error is the input to the controller. So U of S equal to Kp plus Ki by S plus Kds into E of S. Therefore, U of t equal to Kp E of t plus Ki 0 to t E of tau d tau plus Kd d by dt E of t. So when G of S equal to 1 by tau divided by S plus 1 by 2, which is our standard first order plant. So L of S equal to D of S into G of S.
Excuse me, sir.
Yes. Oh, sorry.
Sir, you are not presenting, sir.
Yes.
Since the starting.
So in this PID controller, we have Kp plus Ki by S plus Kds. So output of the controller is called the control law. That becomes the input to the plant. Error is the difference between R of S and Y of S, and that is the input to the controller. The control law is proportional to error signal plus Ki times integral of the error plus Kd times derivative of the error. So that means you have more degrees of freedom to tune your controller. You have more flexibility. So G of S equal to 1 by tau divided by S plus 1 by tau is our standard first order plant. Then L of S becomes a type 1 system. The transfer function of the closed loop system is L of S divided by 1 plus L of S. So it is S square plus S into 1 by tau plus Kd times kd by tau into s square plus kp by tau into s plus ki by tau. So if you check the denominator, coefficients of s square are kd by tau plus 1. So that will be kd plus tau divided by tau. Coefficient of s is kp plus 1 divided by tau and constant ki by tau. Now, if we have to compare this characteristic equation with the characteristic equation of the standard second order form, in the standard second order form, coefficient of s square is 1. Okay, so if you want to do the comparison, we need to divide this characteristic equation by kd plus tau divided by tau. So you remember that when you are calculating roots of the equation, we equate the equation to 0. So since we are equating it to 0, dividing it by any number will not affect the roots. So roots of this equation and roots of, and if you divide by the coefficient of s square, the roots of both the polynomial are one and the same. So we'll divide it by kd plus tau divided by tau. So the resulting expression is s square plus kp plus 1 divided by kd plus tau into s plus ki divided by kd plus tau. The natural frequency is square root of ki divided by kd plus tau. So comparing with the natural frequency, omega n square is ki divided by kd plus tau. So omega n is square root of ki divided by kd plus tau. And zeta is 2 zeta omega n is kp plus 1 divided by kd plus tau. So therefore zeta equal to 1 over 2 omega n kp plus 1 divided by kd plus tau. Substitute for omega n. I want you to use your pen and paper and do these derivations. These are very important. So substitute for omega n. Omega n is square root of ki divided by kd plus tau. So obtain the expression for omega n and zeta. See, our interest is the closed loop system. Why are we in any control system? We prefer to use feedback and we are interested in the closed loop system. We are designing the controller such that, see, the open loop plant does not have the desired behavior. So therefore, the desired behavior is decided by the time domain specifications. Time domain specifications are dependent on zeta and zeta and omega n also decide the pole location. So we are essentially altering the pole location. Open loop plant is not behaving as our requirement. Its pole locations are different. So we are changing this. We are going to obtain a new system whose pole locations will be such that they will satisfy the desired response or desired behavior. That is why we are using controller and putting the feedback, and we are getting this new system. And we are interested in this new closed loop system. We are interested in the poles of the closed loop system, so that this closed loop system behaves according to our requirement. So that step response of the closed loop system satisfies our time domain specification, so that poles of the closed loop system are at the desired location. And standard second order system is only a reference system. We have studied the standard second order system. We have understood its behavior. We have understood how the pole location and zeta omega n influence the step response. So having understood the standard second order system, we will try to have the step response of this closed loop system similar to the standard second order system. So that is why we are comparing with the standard second order system. So it's a kind of a reference system for us. And our main interest is closed loop system. And since the closed loop system is a second order system, we can compare it with the characteristic equation of the standard second order system. In many situations, you will even get higher order system, third order or fourth order or fifth order. Even then, we will only compare the second order system with the standard second order system by considering the two poles which are closer to the imaginary axis. When you consider only the two poles closer to the imaginary axis, which we call them as the dominant poles, you have a second order equation. You can then compare the second order equation of the poles coming from the poles with the standard second order characteristic equation. Okay. So that is, the poles which are closer to the imaginary axis have the higher influence on the system behavior. That is what we studied when we studied what is the influence of extra poles and extra zeros in the system. We have already done that class. Okay. So the main interest is the closed loop system. And here the closed loop system is a second order system. Therefore, we can directly compare it with the equation s square plus 2 zeta omega ns plus omega n square. Is it clear? Any other questions? Any other questions? Yeah, you can further simplify this zeta kp plus 1 divided by 2 root ki kd plus tau. Correct. So that's what I have derived, Kp plus 1 divided by 2 root Ki into Kd plus tau. You can also cross check with our PI controller. In PI controller, no, if you in the PID controller, if Kd is equal to 0, it becomes a PI controller. So I will just show you the comparison. So this is for the PI controller and this is for the PD controller. So if you set Kd equal to 0, it should match with the results from the PI controller. So we will check with a numerical example. We'll do an example, that is G of S equal to 4 divided by S plus 4. So design PID controller such that poles of the closed loop system satisfy theta equal to 0.6 and omega n equal to 10 radians per second. So here the time constant is 1 by 4, 0.25. Can you design Kp, Ki and Kd? In design problems, the solution need not be unique, but some solutions are better than other solutions. Just so I will give you one procedure. So you have 3 Kp, Ki, Kd, and we have omega n and zeta. So you choose Kd value, and solve for Kp and Ki. So depending on the value of Kd, you will get different solutions. Of course, Kd equal to 0 corresponds to PI controller. So give me a solution by choosing Kd, solve for Kp and Ki. So whatever solution you give, I will do the simulation. So G is the plant. Give me Kp, Ki, Kd. I will define the controller. Kd equal to 2. Okay. Kp equal to 26. Ki equal to 225. Is that correct? If Kd equal to 2, so 2.25, so Ki will be 225. Okay. So 2.25 20. This was 12. 12 into 2.25 is Kp plus 1. So 26. So E is equal to Kd square. Kd is equal to 2. Kd equal to 2. Kp equal to 6. Ki equal to 225. So E is equal to transfer function Kd Kp Ki 10. Okay. So L equal to feedback. So L equal to D star G. It's a unity feedback. And GCL GCL 1 minus 1. So this is the transfer function of the closed loop system. So for this system, the step response of the open loop plant without controller Okay, so blue one is the open loop, the green is the closed loop. So there is an improve in the rise time and also settling time. closed loop system response settles to steady state value earlier than the open loop response. Also the rise time. Any question? My solution is, anybody else has given any solution? Okay. I have used KD equal to 3.75 because tau is 0.25. So then division is easy for me. So KI equal to 400. So this becomes 4. So KI has to be 400. So 48 is equal to Kp plus 1. So that makes Kp equal to 47. Solution Kp equal to 47. Ki equal to 400. Kd equal to 0.75. Check whether the damping of this closed loop system is satisfying the design requirement. Design requirement is zeta is 0.6, omega n is 10 radians per second. Any questions? Okay, if there are no questions, I'll just upload these notes on the web page. So for the second test, portion is starts from time domain parameters. it is standard second order system analysis. You should be able to derive step response of the standard second order and expressions for time domain parameters, rise time, overshoot, settling time, and how the co-locations are related to all those parameters. And then stability definition theorem and Routh-Hurwitz test for the stability. Special cases in the RH test. Then steady state error for different types. I may ask a derivation or I may ask a numerical. It can be unity feedback or non-unity feedback. And then designing proportional integral or PID controller. So these are the topics that will be covered in the second test. Any question? Okay, if there are no more questions, we'll stop here.